All right, boys and girls, you should be getting your daily Q done. And then when you're done with that, we're going to start reviewing for our test. Tomorrow in class, you'll have the multiple choice portion of the test. And then on Wednesday, you will have the short answer portion. Just like we've done in the past, we're going to split it up. So remember that this test is going to cover 7, 8, and 9. So we're going to spend some time on 7 specifically today because 8 and 9 are a little bit closer in your head. 7 covered periodic trends. Okay. I did post a list on Canvas of topics for you to go through and make sure you've covered them so that you know them for your test. This is those skills from the end of the chapters. I've deleted some, so this topic list is exhaustive as far as these are ones you actually need to make sure you know, okay? A lot of them are going to involve things that we've practiced over and over and over in class, so you need to refresh your memory on how to do Lewis structures, how to calculate formal charges, make sure you can use those MO diagrams that we worked with at the end of last week, and how to get information from those MO diagrams. Other major topics we covered are things like lattice energies in Chapter 8 and polarity of bonds in Chapter 8. In Chapter 9 is when we introduced the idea that a molecule could be polar or non-polar, like the whole molecule, instead of just a bond, okay? From there, we start Chapter 7 with a discussion on effective nuclear charge. Real quick, I need to take attendance or lack thereof. So no Shelby. No Ben. No Grant. All right, so this guy was the Z effective, if you will. And Z effective could be calculated using a combination of total electrons minus what we call shielded or core electrons. We talked a little bit about how this just meant that Z effective is directly related to valence electrons. How many total valence electrons does something have is going to indicate what its effective nuclear charge is. All right, effective nuclear charge had to do with how closely attracted the electrons are to a nucleus. So for instance, so more valence electrons means higher Z effective and greater attraction. And we should even insert this idea of strength of attraction. Okay. What that means is as we move from left to right, the number of valence electrons goes up, and the attraction for those electrons, the more there are, the more attracted they are. So Z effective also led to, and this is 7.2, a discussion on atomic radii. Okay. This is determined using 2 identically bound atoms, so think like something like HH, dividing the bond distance between the nuclei in half. Okay, so it's how it's determined. The next thing was the trend. Anybody remember what the trend is as we move left to right? Do we increase or decrease our bonding atomic radius as we move left to right? Decrease. Decrease, and we just said because of Z effective. As you get more electrons, we get more attraction. Everything gets pulled in close. Okay, as we go top to bottom. What happens? Anybody remember? It increases. Why? Stuff argument. Thank you. Please put stuff in quotation marks, and when you describe it to me, do not say stuff. Say things like, the atoms are getting bigger because they're gaining a lot more protons, a lot more electrons, a lot more neutrons. As we move top to bottom, we're gaining a large number from one row to the next. Okay, so that was our first trend in chapter 7. Yes?
What does the last part of the left to right translate?
Everything gets pulled in. Why'd you got a little icky? All right, our next trend or concept was ionization energy. Okay, anybody remember what the ionization energy is? Go ahead, Chase. The energy it requires to remove an electron specifically remove an electron, and this part is just kind of like, remember this part, in a gas phase. So I'm going to put a little star here so we kind of remember it. Technical definition of an ionization energy involves the gas phase, because when things are in gas form, that's when they can be ionized. Okay? All right, the energy required to remove an electron from the atom, assuming we're actually trying to remove an electron, we're typically trying to remove it from its valence shell, right? We're not trying to remove inner electrons. We did talk a little bit about what happens when we try to remove a shielded electron, right? We said we saw this quantum leap. It was the correct use of the term quantum leap in change in energy from one thing to another. All right, as we move left to right, what happens? So remember, we're removing an electron. Is it easy to remove fluorine's electrons? Heck no, fluorine wants the electron, right? So as we move left to right, ionization energy, and we're talking about, remember, there were several ionization energies. The first ionization energy is the one we're talking about as far as the trend, increases. Right? Because everything likes the electrons on the right side. It's a good way to remember it. Okay. What about top to bottom? Yes, it decreases. Why? Okay, more stuff means what happens to that stuff? Distance-wise, it gets further and further away. Okay? They get further away from the nucleus and become easier to pop off. Okay, so here's here's an exception alert. An exception alert. Okay, let's say we've removed our first electron from sodium. Say this costs us 1,400 joules of energy. Okay. Now I have Na+, which looks like the electron configuration for neon, if you will. Trying to remove an electron from here, also known as the second ionization energy of this particular atom, would have what we call the quantum leap. Once your atom is in the noble gas configuration it wants to be in, removing another electron requires a lot more energy, a huge jump in energy. Sometimes it's 5 times as much, sometimes it's 10 times as much. It really just depends on what part of the periodic table you're talking. Okay? Okay. Please do remember that this is a first ionization energy because it's the first electron we remove. This would then be what? The second. So do a lot of the atoms that we deal with have more than one ionization energy we can talk about? Yes. The trend only applies to first ionization energies. Okay, so make sure you make a note of that somewhere. Trend only applies to first ionization energies. Okay, now we do the next one. The opposite, if you will, of the ionization energy is the electron affinity. So if we're talking opposite, what does that mean? That an electron affinity is exactly what, Emily? The energy that is either released or gained from the surroundings when an electron is added. The value can be positive or negative. Which type of value indicates an electron is being added and it's favorable? May you remember? This means it's favorable, or, if you will, spontaneous. It means it gives off energy when it happens, so it's likely to happen on its own. Okay? All right, let's talk about the trend. Happens left to right. Does it become more favorable, or does it become less favorable to gain an electron? Becomes more favorable. Okay? What that means is that values go from positive to negative. Yes? More? Oh, spontaneous. Sorry. I'm trying to film this on my phone because my computer's still updating. It's not going well. My phone keeps moving. It doesn't want to participate today. All right. From positive to negative, what about top to bottom? What do you think? Top to bottom. Hold on. I'm gonna find my table. I like to look at the periodic table. Because I'm pretty sure this is one that doesn't really there's like a kind of a trend. Kinda is what we're gonna say here. There's a kinda trend, and it's that it gets less favorable. Again, a kinda trend. So like for instance in the halogens, fluorine has a value of negative 328. Chlorine has a negative 348. I'm sorry, 29. Bromine has a negative 325. Iodine has a negative 295. So again, a kind of trend. Okay. More importantly, you can talk left to right. Okay. In the end of this chapter, we talked about individual groups and some of the trends within individual groups. So for instance, in something like the difference between metals and nonmetals. Okay, what do you know about metals? What are some characteristics they always have? They're shiny, they're conductive, they're malleable, they're ductile, meaning they can be pulled into thin lines. Just some general trends and the differences between metals and nonmetals. And then the metalloids and what they have in common with both, right? Then we also discussed in this one different groups on the periodic table. Groups meaning like alkali metals, alkali earth metals. 7.7. On the periodic table, we have groups of elements that have properties in common. The first is group 1. Group 1 has the alkali metals. The alkali metals tend to have lowest ionization energies in the first order. They have the highest second ionization energies, but that shouldn't matter. Low melting points. And low densities. They have pretty reactive properties with water. It's the one we watched where they were like dumping chunks of metal from a distance and then running, right? From there, we talked group 2. These are called the alkaline earth metals. The term alkaline means basic. They form bases readily. When you think the term base, you've heard of all kinds of different bases, but a lot of them come from this particular group of metals. Typical 2+ ions, they have the They're pretty reactive with nonmetals. They're all metals, so they also have the other common properties of metals that you would expect. Shiny, ductile, conductive, etc., etc. Okay. Both of these groups form compounds with H, the hydride ion. So in the case of these things attached to a hydrogen atom, hydrogen becomes the nonmetal with the negative charge. All right. 7.8 talked about halogens and noble gases. Aside from everybody wanting to be like a noble gas, the noble gases are pretty boring. There's not much to say about them other than that they are unreactive, also known as inert. Okay. The halogens, on the other hand, do tend to be reactive. One of the most common sayings about chlorine is that it'll bind with anything. Tends to find something positively charged and bind with it, because why not? Has one electron that it's willing to gain, will do anything to get it. Okay, that was chapter 7. Questions in chapter 7. One of the things I kind of skipped over, but I'm hoping we understand, is the difference in atomic radius and ionic radius. So when we talk atomic versus atomic means no missing electrons, right? Ionic means we've either gained or lost an electron. When chlorine gains an electron, it becomes Cl -1, right? It has some atomic radius here. What happens to its atomic radius when it gains an electron? It goes up. We're gaining an electron, so our atomic radius is going up. Gaining something means increase. Okay? What about with sodium? Tends to readily give up an electron. What happens to its atomic radius? It goes down. Right. Giving up an electron makes our atomic radius or our ionic radius smaller. Okay. That was all for chapter 7. Chapter 8 is on bonding. Basic concepts of bonding. The two major ones we focused on in chapter 8 were ionic and covalent. What is the difference between an ionic bond and a covalent bond? Yes, Patrick. Correct. Ionic bonds do what? It's an electrostatic attraction. So positive likes negative. They're just attracted to each other. The first major topic in chapter 8, ionic bonding, introduced the idea of a lattice. So if you are dealing with an ionic bond, which is a metal plus a nonmetal that are experiencing we have to deal with a lattice energy. And a lattice energy is impacted by charge and size of ions. So here's one type of ionic bond we can be dealing with. Low charges, small sizes, they're relatively high on the periodic table. Another one we can be dealing with is something like this. Between these two, which molecule has the higher lattice energy and why? Okay, I've got bets on this one, but why?
It has a
Higher charges,
and the ions are larger.
higher charges, and larger ions. I like it. Okay, that was lattice energy. The next type was covalent bonding. Where we were sharing electrons between the two atoms. What more can I say about covalent bonds? Is the sharing always unequal or equal? No. Can be equal shared. When things are equally shared, what kind of bond is it? Non-polar. Can be unequally shared. And that would be a polar bond. My previous lectures should be up for you to access at this point. So I recommend you go back into chapter 8 and look at some of the electron density diagrams. Remember we had seen like these like awkward looking like eggs. And like on one side of the egg you had all these different colors and on the other side you had a completely different set of colors. That was an electron density diagram that described why that bond in particular was polar. Okay? From there, we talk Lewis structures. Section 3 was on how to draw Lewis structures. How do we draw a Lewis structure? Count electrons. Put the least E neg atom in the center. We never put hydrogen in the center. Another piece of advice, when in doubt, carbon in the middle. If your atom has a carbon, put the carbon in the middle. End of story. We fill outer octets. If out of electrons, fill the inner octet with double bonds. If we have leftover electrons, add to the center atom. So for this particular structure, I have 24 electrons. 24. So I've filled in my structure with my 24 electrons. Does my center atom have an octet? No. So I create one. Okay, from there, we learned about, well, this is like way out of order, but let's do resonance. Is it resonance or no? Yes. So what other atoms should I be drawing?
Where the double bond at changes the formal charge, correct?
It changes the formal charge of just that particular oxygen, yes. Yeah, so this is section 3, and in section 5 and 6 we introduced Lewis structures and resonance. I'm sorry, resonance and formal charges. So it does have resonance, so we draw all the resonance structures, then we do formal charges. Let's just do one structure of formal charges. I'm going to do this guy. This is total number, remember it's number of valence electrons per atom minus the total number of dots and lines around that single atom. So I'm gonna do this structure. For the nitrogen has 5 valence electrons. It has 4 lines. So my nitrogen has a +1 charge. When we distribute formal charges in a structure, where should the positive charges always be? What atom? Outside or inside? Inside. So since this is on the center atom, this is okay. Where do we want our negative charges to be if we have them? On the outside. I'm going to do O's 1 and 2 as this one and this one because they're identical. They have the same kind of setup. I'm going to start with the 6 valence electrons that an oxygen should have. Then I'm going to subtract the number of lines and dots, and I'm going to get -1. Is the oxygen the atom in this structure that can have the negative charge? Yes. So I'm going to say this is okay. This is O2. This is O1. I like to put them in my structure so that I can keep track of what's going on. Our last one, oxygen 3, has a formal charge of 0. Okay, so this structure altogether has a negative, a positive, and a negative charge. Do they sum to be the overall charge on the atom? -1 plus 1 minus 1 is -1. Okay? Should it have the overall charge on the atom when you add them all together? Yes, it should. Is this structure optimal? Would it be nice if we could make it so that only one thing had a -1 and everything else had zeros? Yes. But is this structure obeying our rules? Yes, it is. Does it have an overall -1 charge? Yes, it does. Does it distribute the charges the way it should? Yes, it does. Okay. What next? Trying to think. Okay, so the other thing we talked about in this one was bond polarity and the idea of dipole moments. We also had bond enthalpy in this chapter. So remember, you're looking for bonds broken minus bonds formed. There are some practice problems in the end of the chapter. If you do the red one, the answer's in the back of the book. That was the very last thing. How do we determine the polarity of a bond? What do we use? Be more specific. Electronegativity. He beat you to it.
Is that the correct number?
Say again?
Like that one periodic table in the book.
Yeah, it has the values for electronegativity, yes. Remember that we said if the difference in the electronegativity is from 0 to 0.5, you have a nonpolar bond. If it is from 0.6 up to 2.0, we have a polar bond. And then if it is 2.1 or greater, it is ionic. Okay. From there, we discussed this idea of a dipole moment between two atoms only. Okay, so this chapter focused on in the bond. Chapter 9, as we discussed last week, talked about the overall molecule having a dipole moment. And the only way a molecule has a dipole moment involves what? If it's polar. So a polar molecule has a dipole moment, and we determine that by looking at the molecule symmetry. If there's lone pairs on the atom, it means we probably have a dipole moment to contend with. If there's no lone pairs and everything attached is identical, then we probably don't have a dipole moment because it's symmetrical. Okay? But here we introduce this idea of a dipole moment in a single bond. Okay? And in this particular bond, the difference between the two is not that great, but it's great enough that we have what we call a dipole moment. The arrow points in direction of most electronegative. In case you're wondering why the arrows get drawn the way they do. The arrow always points towards where the most electron density is. Okay. Remember that these are only for polar molecules. Oh, let's see the legit spell there for a second. All right. Okay, last thing in this chapter was the equations you'll be given for this particular exam are on this sheet. Make sure you look at them. But delta H of a bond is going to be equal to the bond on the face of everything broken minus everything formed. Where do the numbers come from for that particular type of a problem?
They're given.
You have to be given them, right?
Yes.
You're not just supposed to know that off the top of your head, okay? You have to be given that. For chapter 9, the one you're going to get is bond order. At this point, hopefully you're pretty familiar with bond order, but if you're not, you'll get that. You'll also never be asked to actually draw the molecular orbital diagrams. I would give you one to see. Yes?
So what were the possible math things that can be done with like, oh, and that depends on those two.
Because like if you,
I was thinking about the first delta H. Never mind.
that's, yeah. So this is like the fourth way we've learned to calculate delta H.
Yeah, I know.
Yeah. So remember it's like this plus.
Yeah.
So what would you do? You'd look for all the stuff broken, so that's the stuff on the left side. Breaking these two, forming these two. Then you would calculate your values from the table. So you'd have to have the values for a CH bond, a CL-CL bond, a CCl bond, and an HCl bond, right?
When we were doing it in class, we were just breaking them all up, though, right?
Yep, so remember there's two approaches. One is identify the things you know are breaking and the things you know are forming. The other is to just break everything on the left and reform everything on the right. You choose your method, both will get you the same answer. Yes?
Is the whole test tomorrow or is it split up?
Just the multiple choice tomorrow. Good question. What other questions do we have? Your time starts at 7 minutes. I love 7 minutes. All right. What in chapter 9 would you like me to do again?
I don't know.
We did it last week, so
Was that like geometries and stuff?
yeah.
Are we gonna have to like draw those?
No. Would you have to name them?
Like all of them?
Are you going to be able to see that if like you have this atom, that it's tetrahedral? Absolutely. That's fair.
Oh my
Wait, what's
god.
the what's the
Yes.
three? I'm blanking.
3 is trigonal planar. 2 is linear, always. Yes.
I know all the basic structures, but
You know the electron geometries.
do we have to know names of like the fancy stuff like
Yes,
that?
you do. I would say focus more on anything with 2, 3, or 4 bonds, right? So linear up to tetrahedral. Anything beyond that would kind of be like a challenge version of the problem. I don't think I've ever put an octahedral problem on a test.
So you said linear?
Linear, trigonal, planar, tetrahedral. Make sure you know the electron geometries and molecular geometries of those 3 specifically. If you're trying to get the bonus points, you better do the bipyramidal. What is it? What is it? Hold on. Hold on, hold on. Is it trigonal bipyramidal? Is that what it's called? Yeah. Aha. Yes. That's the 5.
So, we're gonna have to name like the weird things like seesaw, like that.
Electron molecular.
Seesaw too.
Seesaw is in the 5.
Wait,
So.
we need to memorize the angles.
Seesaw is that there's 2 bonds.
Yes, you need to know the angles.
Oh my god.
It's not like we spent a whole week on it. Okay, so the linear. So this is total number of domains.
I'm not ready, I gotta draw that.
You have it in your notes. We went through and drew them by hand in our notes.
I know what I'm doing.
Linear. What's the molecular geometry of linear?
Really
Linear.
Seesaw.
Linear. Seesaw is like way down there. Don't just yell seesaw for everything, please. All right, for 3, what's our electron geometry? Trig, planar. If you have 2 bonding, 1 non-bonding, remember what the terms non-bonding mean?
Long hair.
Yep.
I know that.
If we have 2 bonding and 1 non-bonding, what is a trigonal? Yep. If all 3 are bonding, it's still trigonal planar.
Whoa. Well, that makes sense. That makes a lot of sense.
I'm gonna add in
Gonna add in?
hybridization. Oh, yes, you can do this. If it's linear, SP, SP2, SP3, D. You've done them all before, like 4 or 5 times each. What did you think we were doing it for? Health? Come on.
I'm focusing on getting
Scared of naming them.
All right, 4 was tetrahedral with 2 and 2. Do you need me to write bonding and non-bonding?
No.
Can I just write B and NB? With 2 and 2, bent. With 3 and 1, nice.
I'm looking at my notes.
Trig pyramidal with 4,
It's just
tetrahedral. Okay, before we move on, because these are the ones. Stop it with your seesaw. You're not there yet. Before we move on, let's talk about angles. Oh, you poor babies. Linear, bent,
I got quiz
less than 120. Why? If it's bent, it's got a non-bonding lone pair. And what does the lone pair do?
It swishes it.
Squishes everything. What about a trigonal planar? 120.
Yeah. Okay,
I would say make sure you know the electron geometry of 5 and 6 for sure. You should know them already. Trigonal, bipyramidal, octahedral. Don't worry about molecular geometries of those things. Study hard.
Yeah. Maybe you know what time it
See you
is.
tomorrow.
Maybe you know what time it is.
It didn't affect me in the least. I got through 2.5 chapters of review in 45 minutes.
I got a quiz.
I didn't need a clock to do it.
I got quizzes to make now.
Yes.
Or
Down here. T-shaped is one of these guys. So you don't need to know the molecular geometries of 5 and 6. You just need to know these two. So this one is what? Trig bipyramidal. Go through the list. Study. You know more of it than you give yourself credit for. I'll tell you.